lecture in the second section of Organic Contaminants in the Subsurface Environment. In the first lecture in this section, we introduced the idea of monitored natural attenuation, a remedial technology which makes good use of the natural processes. It gives us a good basis to discuss the natural processes. So we mentioned the four processes that we're going to emphasize: advection, dispersion, retardation, and reaction. We want to move ahead in this lecture talking about monitored natural attenuation, but emphasizing the advection process. Advection is quite well known in hydrogeology, but sometimes we don't do it well. And when we don't do it well, we end up with badly monitored natural attenuation. And in this lecture, we'll start giving you some examples of mistakes we've been involved in. Advection is the movement of groundwater that carries the contaminants along. And hydrogeologists have been dealing with advection for many, many centuries now, it appears. Here's an example. If we have a map of an area in which the hydraulic head of different wells is produced, as you see here, and if we ask ourselves, which way is the groundwater flowing? Hydrogeologists can usually get a sense of that very quickly from a map like this, because groundwater moves from areas of high head to low head. Head is indicated on the map as meters above mean sea level, so groundwater is flowing from areas of high numbers to low numbers. So, having a look at that map, I think you would decide that water is flowing from the upper right-hand side to the lower left-hand side. The next idea is to try and determine more quantitatively if that's the right flow direction. So hydrogeologists interpolate between the data points and draw contours of the water levels. So we've done so here. Your interpretation might be slightly different than mine, and again, that's typical for hydrogeologists. The next question is, which way is the water flowing? We usually assume the material is fairly homogeneous, and in that case, the water flows at right angles to those contours. So water then is flowing from the upper right to the lower left, as we've indicated on the diagram. The next point about that is really, how certain are we of that flow direction? Well, each site is different. In a more complex site, our certainty goes down. If the number of wells is few, then we have large uncertainties. In this case, we might decide that we have perhaps a 15-degree uncertainty. That is, the groundwater may be flowing 15 degrees one way or the other. Or in some cases, it might be 30 or 40 or 50 or more degrees. And hydrogeologists have to anticipate that uncertainty and make sure that their interpretations are consistent with that. The next question, of course, is then, how fast is the groundwater moving? And geologists and hydrogeologists use Darcy's law to do that calculation. Here's Darcy's law, and we can apply it to this example. Again, we show the contours, groundwater flow direction, and we have to calculate the velocity. Here's an example of some data. The hydraulic conductivity, K, is given as 10 to the minus 4 meters per second. Porosity is 0.3, a typical sand aquifer. Assuming the material is homogeneous, we can use Darcy's law. So the velocity of the water is equal to hydraulic conductivity times the gradient, but importantly, divided by the porosity. So let's plug our values into that equation and see what the groundwater velocity is. So in the next line, we've plugged those values in. We do the calculation, and we see that the groundwater is moving 2.8 meters per day. Again, I think we have to ask ourselves, how reliable is that number? Could it be 3? Could it be 5? Could it be 20? That again is an interpretation the hydrogeologist has to come up with. Depends on the quality of the data, the consistency of the material, and again is site-specific. Typically, I think hydrogeologists anticipate that they might be wrong by perhaps 50%, or maybe 100%. So again, when you interpret the flow of contaminants, remember that our velocity may have considerable uncertainties. And that may in fact be the biggest uncertainty in our project. So we can always try and do better, but the important thing is to acknowledge that uncertainty. And that leads us towards badly monitored natural attenuation. And this is where we make some mistakes, or we don't really recognize the limitations in our field data. So what we'll do is look at an example. What we want to do is look at the distribution of the contaminant along the flow path. So in this case, we'll plot concentration versus distance along the flow path. And let's make up a site. Here it is. It's a plan view, so we're in an airplane looking down. The red area is the contaminated area. The groundwater is flowing from left to right, and the contaminants are being picked up by the groundwater and making a dissolved plume. And we're asking ourselves, how far has the plume gone? Is it still safe? Is it likely to be safe in the future? Those sorts of questions. So we think we know the flow direction, and we then put wells along that flow line to find out where the plume is. So we've installed those wells, and those wells have different concentrations. We plot them on the diagram. So the well up gradient of the source has no contamination. That's good. The highest contamination is immediately down gradient, and the contamination drops off as we go further down gradient. That's what we expect in natural attenuation. And in fact, we may draw the plume as something like this, where the front of the plume, the front of the contaminants, is somewhere between the last two wells. Well, if I was a well owner down gradient, I would be happy with that analysis. I would be satisfied that the contaminants have not reached my well, and that you could monitor and assure me that the contaminants aren't reaching my well. The question really is, what happens if you're a little bit out in the flow direction? Let's look at that same case with the same wells, but let's assume that the flow direction is about 15 degrees different. That's only a little bit. Maybe makes a difference though. So here's the actual flow direction, and we have the real plume then flowing in that direction. Now, this plume, which unfortunately extends a long way, in fact fits the previous data very well. Same data, very different outcome in terms of the plume length and the plume location. So if we compared the assumed plume distribution to the actual plume distribution, shown in red here, we see that they're similar until we reach the end of the plume, and the contaminants now are clearly beyond that last well. I no longer have assurance that the contaminants are not reaching my well, so I'm not very happy. And that's only because we didn't get the flow direction very precise. Of course, in the real world, you wouldn't design your monitoring in that way, but that shows us that flow direction is really important in order to apply monitored natural attenuation and assure people that their well is protected. We can also have other ways of badly monitoring natural attenuation. Here's a second example. It's based on some cases from Texas. In this case, they drilled in a shallow sand aquifer, and every well they drilled encountered an aquitard at depth. And so logically they assumed the aquitard was underlying the whole site. And in those wells they measured contaminant levels down gradient, identified a plume, and identified that in fact it wasn't extending very far. Again, we've shown the distribution of contaminant concentrations along the length of that plume. The reality turned out to be that in fact the assumption that the aquitard was consistent and continuous was in fact wrong. Subsequently, they found out there was a hole in the aquitard, and the plume actually went down into a lower aquifer. The hydrogeologists anticipated that might be the case because the vertical hydraulic gradients were downward when they measured them between the two aquifers. So there was always the potential the plume could go deeper. And in this case it did. So when it went into the lower aquifer, we are no longer monitoring it. So that was a big problem. The plume was further than we knew, and it would be actually quite difficult to monitor that plume because it's deeper, more expensive, perhaps less certainty. So in that case, if we hadn't recognized that hole in the aquitard, we would be doing badly monitored natural attenuation and not getting the story correct. So in the next lecture, we'll talk a little bit about another example or two, staying with advection, and then we'll move on to dispersion.